Hi, my name is Stefan Goebel. I'm the general manager of Arnold Glas Corporation in North America. We're an architectural glass firm based out of Germany, produce at 8 production locations, and we have our own coating lines, Archon. So the coating brand is Archon that produces sputter coatings out of Germany. So we're going to be talking about low E coatings today and the color and performance of low E coatings. Hannes has developed a lot of understanding about color, so there's going to be just a very short brief introduction of the aesthetics, which relates to light and color. Then we're going to be moving on to the makeup of a sputter coating. So you're going to be looking at the different layers of a macrotron sputter coating and how these coatings impact the color and the performance. And then I want to focus on the application, how we can use these coatings in buildings to make them more energy efficient, more comfort, and to conserve wildlife as well. Now, every project starts with a project specification, visible light performance, reflection, solar heat gain, U value. 2 values really stand out there. It's the visible light for comfort and the solar heat gain performance to keep the peak cooling loads manageable in the summertime. Then there's generally a sample review for the aesthetics, and if this meets the requirements of the project, great. But the truth is that in a lot of cases it doesn't. The industry offers different coatings that can meet a very wide, broad band of visible light transmittance and solar heat gains performances, but they come with certain aesthetics, with certain colors. Now, if the solar heat gain performance visible light is met, the color might be slightly silver. Once you move to a slightly bluish color, if that's what's desired, the performance changes. And I want to show you how we overcome this challenge with a process that we call design your own coating. And we're going to be starting off with a very simple question, I think, for this audience. But what color does the sun emit? Anyone knows? No. I get very mixed answers usually. Well, it appears yellow, and the reason that it appears yellow is because the surface of the sun is about 10,000 Fahrenheit. And yellow light at about 550 nanometers emanates off material that temperature. But as you might imagine, as you think about a rainbow, the sun emits all light. In fact, it emits about 4% of ultraviolet light, about 46% of visible light, and beyond this is infrared light. So what we're trying to do is with the coatings, we're trying to let as much visible light pass through the coating and reflect the infrared light. And one thing that Hannes mentioned earlier that I want to point out too is important. There's this belt-shaped curve right starting at the visible light to the end of the visible light at 720 nanometers. And it shows how the human eye sees. And it sees more sensitive in the color ranges of about 550 nanometers than it does at the edges about 700 or 380 nanometers. Now, once the light hits the retina, it's processed into different colors. And these colors can basically be broken down into 3 parameters. It's the hue, the color, the saturation, which we heard earlier, and it's the value of brightness. And I'm just going to go over this very quickly because Hannes mentioned this already. We work in our industry of the CIEL color space that allows objective color measurement. And we're looking at the color space, the 3-dimensional color space, green to red A, B to yellow, blue, and L, black to white. And we're going to simplify this. We're breaking it down to a 2-dimensional color space, which is just taking out the L value, with a spot right in the middle being neutral. Now, moving on, once the coating has been specified for a project, we learned that there's an L value, an A value, and B value to define the color. And we want to make sure that we don't deviate too far of that value. And this is defined by the delta E, which is the total of the delta L, brightness, delta A and B, the color. However, we need to consider that the human eye doesn't see equally sensitive for these different values. No, we see more sensitive for color changes than we do for saturation and than we do for brightness. Now, this color box is showing this delta E, but what it really should be a color ellipse. It should allow for more differences in brightness than it does for color. And the bottom line of this slide really is that for a project, it's important to consider the individual delta L, A, and B values, because you might end up with a very low delta L value that doesn't factor in as much to the color difference, but a high delta A and B value, which the human eye is more sensitive to. But you might still be within that, well within that total delta E value. So that's the bottom line of this. And we heard this earlier, some colors allow for more differences than other colors. Now, moving on to the performance part of this presentation, I mentioned earlier the solar heat gain performance is important. And this is just a quick refresher. Solar radiation hitting the glass, some is transmitted, some is absorbed by the glass, and some is reflected to the exterior. Now, the solar heat gain performance is the total of the direct transmittance and the convected heat to the interior. The magnetron sputter coatings that we produce, they in general, magnetron sputter coatings, they offer high flexibility to the layer design. And the layer design defines the properties of the coatings. And this is a very simplified concept of a double silver coating. We have the overcoat that's required for the durability of the coating. We have the base and top layer, which is important for the mechanically and chemically durability of the coating. We have the primer, who protects the silver coating during the sputter process. And then we have the silver coating that mainly impacts the solar and thermal performance and the reflection. So moving on, we're going to be talking about the reflection, the transmission, and the absorption of the glass, which make the performance. And we're looking at this wavelengths graph here, and what we see is the ultraviolet light, about 260 to 380 nanometers. We have the visible light, and then we have the infrared light. And what we're trying to do is, so this coating, this is an example of a coating that I brought with me that offers about a 52% visible light performance, about a 30% reflection, and about a 25% solar heat gain performance. And if you look at the A-B matrix, you can see that we're right in the middle of this coating, which means it's a fairly neutral coating that we try to develop here. And you can see here we took pictures of a sample without the low E coating and with the low E coating. So it's very neutral in color, but high reflection as well. Now, if we want to create a coating like this, what we need to do is we need to reflect a broad band spectrum of colors. And this is red on the right side, from 0% reflection to 100% reflection. And what we're doing is we're reflecting the green, yellow, blue, and red light, because the human eye sees more sensitive in the yellow, bluish, greenish areas. We don't have to reflect as much light in order to create these colors. Now, in the red area and in the purple areas, we need to maximize the reflection so that all these colors factor into the overall color. And if you mix a lot of colors, you generally end up with a neutral color. The next example that we're looking at, and this is just a picture of a project that shows this performance and the color of the coating. The next example that we're looking at is a coating that offers about a 25% visible light, about 36% reflection, highly reflective, and about 26% solar heat gain performance. And you can see that we're right up there in the yellow, orange, red color. And what we wanted to create with this coating is a gold coating. And what we needed to do is we needed to reflect a maximum of light in the red and the yellow and the orange, because the human eye does not see as sensitive in these colors, so we need to reflect the maximum of these colors, right? And this is what the coating looks like that we developed here. This is an example of the project itself, which is in Dubai. Now, we can create essentially any color on this color spectrum, and we've created a lot of colors over the last 30 years, but I want to move on with a different idea at this point. What if we have one color, but we want to create different performances with that one color? As you remember earlier, there's this challenge where we might like a color, the architect, the client might like a color, but it comes with a certain performance that does not meet the project energy requirements. And the example that I have here for you is 4 coatings. One coating that offers a 69% visible light, one a 61% visible light, one a 52%, and a 42% visible light. Again, what we're looking at here is the uncoated glass, and this is the coated glass in reflection. And you can see how similar they are in color. Of course, once we're going down from 70% visible light down to 40% visible light, the solar heat gain performance decreases as well, and the reflection slightly increases. And I want to give you one example how this was done. Example at the 62% visible light and the 42% visible light. Now you see this curve here. It reflects a maximum of light in the blue and the purple area, which creates this color. If we move on to the 42% visible light, simply what we needed to do here is we needed to keep the same shape of the performance of the coating, meaning we're reflecting the maximum of light in the purple and the blue range, but we're increasing the reflection to a 22% and thereby decreasing the solar heat gain performance. And now we're moving on to the application of these kind of coatings. So what if we have different coatings with one color? As you know, the solar heat gain performance reflects the substantial amount of solar radiation and reduces the heat gain. I talked about the challenge of desiring high visible light, but relatively low solar heat gain performances to keep the cooling load manageable. So there's a challenge between finding the balance between these different performance criteria. Now, in most projects like this one, the Soccer Tower in Baku, the solar heat gain performance, and in this case it was a 28%, is defined based on the south-southeast facade of the building, which is where the sun is angling around the building, so it's exposed to most direct heat gain. However, in this project, like in most projects, the design team found the coating that was desirable for the color and the performance, and they put it around the entire building. But that doesn't make so much sense because the north facade barely gets any sunlight. So the north facade could allow for higher solar heat gain performance and thereby could have more visible light for comfort. And this is the example where we would have met this coating requirement, solar heat gain requirement of 28% with a coating that comes with a 27% solar heat gain, about 50% visible light, and then increase the visible light on the north facade of the building at about 20% in this particular example. Now, the same concept works with these buildings, high-rise buildings that are shaded by neighboring buildings. There's a lot of heat gain going on in the upper levels of this building, which requires a low solar heat gain performance. Now, once you're going down into the building, it gets extremely dark, and we see this many, many times. So we are able to, by maintaining the color, but increasing the visible light, increasing the comfort in these lower areas of the building at 20 to 30% of visible light. Now we're going one step further at this point, and this is something new that we're introducing to the market in the beginning of next year. What if we were able to have these visible light performances from 70% visible light down to 37%, solar heat gain going from 37 down to 18% in one single IGU as a graded blended coating, which is new. So what we did here, we went from 70 to 34%, and you can see that the upper area of the glass, which has a 70% visible light, it appears bluer than the lower areas, and that's just simply because the reflection increases during the course of the glass pane. But we kept the color as consistent as possible going through this one pane of glass. This is another example, and you will see here my two colleagues. This was the AIA in Las Vegas a couple of months ago. Simon Potts and Lisa Schoen. And the interesting part is how their bodies simply disappear going down that pane. So there's a very high reflection in the upper area of the part, and then we're grading it down, going to a very high visible light performance. Now, what are the applications for this? Anywhere where we're using ceramic frit, anywhere where we're grading. So it's for custom designs, but also for increased privacy. When you think about floor-to-ceiling glazing, there's a lot of glare happening. So avoiding glare and avoiding a lot of heat gain in particular areas while maintaining high visible light performance and a uniform color. Now, there was a presentation about bird-friendly glazing, a very informative presentation 2 hours ago. So I'm not going to go into details, but for those who haven't heard it, it's a big issue, especially in North America. It's estimated that up to 1 billion birds die because of bird-window collisions. It's about 10% of the bird population. Who has ever seen a bird collide with a window here? you want to raise your hand. Who has seen a person walk into class? Who has walked into class? All right, so some of you have more experience with it than others. I've walked into class as a kid. But this is a serious issue in North America, and North America has responded. San Francisco mandates bird protection glass, Toronto mandates bird protection glass, Chicago, and soon to be New York City, in particular areas of the facade. Now, we've heard about the issue earlier too. It's basically the reflection of the glass in some areas where the sky is reflected, the bird sees a flight path and flies right into it. In other areas, in corner situation, walkways, it might be the transparent characteristic of the glass that's an issue. Now, in order to avoid it, what we need to do is we need to break up the reflection of the glass. We need to create a pattern that stands out to the bird so that he doesn't see a flight path. And the presenter earlier talked about the different methods. One was ceramic frit, printing, but I wanted to introduce you to a different concept that he, by the way, mentioned as well. It's a UV reflective coating. And when we started working on this in the late 90s, we followed two theories. On one hand, that there's a certain spider species, the orb weaver spider, that uses ultraviolet reflective silk on the web to deter birds from flying into the web, so it can maintain the web. On the other hand, we know that humans cannot see in the ultraviolet spectrum, but birds can. So the idea was to create a coating that reflects an increased amount of ultraviolet light in a certain pattern, and we tested different patterns. We tested lines, we tested the spider web pattern, that is visible to the bird but not to the human. Now, when we're talking about not visible to the humans, it's extremely important that we are considering this glass to be installed in a building. If you were to look at it into a certain angle, depending on the lighting, you will see the coating, you'll be able to find it. But if it's installed from the inside to the exterior, it almost disappears. And this is an example about the Stanford University, Vassar College. There's a lot of projects such as those. And so we're almost finished today, and we're moving on to the more casual part of the presentation of the day. So I figured it's appropriate to show you this short video. Oh, can you turn on the tone? Yep, I'm going to stop this for a second. Should we try it again? No. That's all right. I think we can play it without the tone if it doesn't work. It's very short.
Hey, watch this.
Hilarious.
All right. Funny. Well, thank you very much for your attention. If you have any questions, please let me know.
Fine, thanks. Yeah, he asked already for questions.
What's your recommendation in order to control the color behavior and tendency? Yeah, because the delta E not control the color behavior and tendency.
Yeah. So I think the color behavior, we heard, you weren't here, Hannes, the presentation before was about color. The temperature of the sun during the course of the day, for instance, changes. If it's a cloudy day, if it's a sunny day, so the facade will appear differently. And we've looked at examples that Hannes showed earlier at different times of the day, different angles. The color variates very, very much. And what we're currently defining is a delta L, a delta A, and a delta B under a certain angle, under 6,500 Kelvin. And that's what it's measured. But it doesn't really reflect what we really see in the facade under certain different daylight conditions. And I think there's a point to be made that we need to think about the way we're measuring the color in coatings. And I believe that was the bottom line of Hannes's presentation, if he's still here.
Okay, one more comment?
In reality, the LAB is not enough to solve the color problem. Yeah, Yeah, we have many problems with metamerism. Yeah, and we have a many problem with birds collisions because we have no tendency and color behavior control. In my opinion, CMC is another method to
Or CIE
evaluate.
2000. Yeah.
Is better than LAB.
Yeah.
More,
Yeah.
more efficient.
Yeah, it's used in different industries to define the color. Yeah. Yeah.
Thank you. That was a very interesting presentation. Especially the gradient coating concept is really intriguing. I was wondering if you spoke about how you are able to maintain uniformity of the color of reflected light, but the intensity of reflection changes as you reduce the visible light transmittance. Would there be a possibility where you could still alter the visible light transmittance and maintain the color and the reflectivity from the outside? So that there is actually no real visible impact on the exterior?
So the short answer is no, not over this wide of a spectrum. But if you compare the first two coatings, one is 13 and one is 13.8% reflection, so they're extremely close, but not over such a wide spectrum of coatings. Yeah.
I mean, we have often employed a gray coloring or gray colored coating to suppress reflection. And I wonder if there would be a way of combining a gray colored coating as a gradient in addition to further bring down the reflection. But I'm just thinking.
Yeah.
But it's very interesting. Thank you.
Yeah. Okay.
Okay, ideas, good. There's another question.
I have a question on the graded coatings and just wondering what is the extra over on having a graded coating, but in terms of fabrication, and also if there's a cost uplift to just a standard single coating on it.
Right. So what we're currently planning is the market introduction officially in North America is next year May, where we'll be showing it at the AIA in Los Angeles. But the idea is that it should be cost equally priced to a low E coating. However, you need to imagine there's a change of settings of the machinery. So we're thinking about the setup cost as an upcharge, but the coating itself, once it's defined and designed, there would be no upcharge.
Okay, Stefan, thank you again.
Yeah, thank you.
Hi there. Did you like what you just saw? If you did, why don't you like the video, drop us a comment below, and share the video as well, since GPD is all about sharing. And to receive more videos in future, subscribe to this channel and don't forget to click the bell icon. Ciao!